Yep. Okay,
If I
take
can
it
just
away.
find, I just find my mouse now. That has disappeared. Okay, give me 1 second. Sorry for this. Okay, I guess I can click on this. That works. All right. Hey, everyone. For everyone who doesn't know me, I'm Julius Busecke. I'm by training a physical oceanographer. I'm currently senior staff at Columbia, and sort of my two main jobs there are the manager for data and computing at LEAP and the lead of open science for M²Lions. Both of these are sort of machine learning for climate science oriented projects, and I do a lot of the cloud native tech support, etc. I'm also a developer. Some of the packages that people might know are XGCM or CMIP, long-term sort of Pangeo fan user and member, if you can say something like that. And I think what's sort of most relevant here is I'm currently sort of the maintainer of the Pangeo CMIP6 Zarr stores, and that's what I'm going to talk about mostly today. Just a really quick intro. What is CMIP? So CMIP stands for Coupled Model Intercomparison Projects, and basically CMIP provides the output of many large climate simulations that have been sort of run under coordinated scenarios or boundary conditions. It's really sort of they originate from all over the world. So you can see in this map over here. Each of these model uses slightly different implementations, parameters, and codes. And we can use these projections under these sort of control scenarios, like, for instance, emission and other parameters, to sort of sample the uncertainty of climate projections, and thus improving the quality of our scientific conclusions that are then presented in things like the IPCC report. And these results are openly distributed via the Earth System Grid Federations as netCDF files following the CF convention. And I just want to sort of prepend here that, like, this has been, I think, in my eyes, a huge success, and I think there's like big credit due to all of the work that folks at ESGF have been doing. I think it's quite incredible to sort of see a really global effort to distribute this data, and a lot of amazing work has been done with this in the past. So then you might ask, I'm going to talk about today about why why we would move CMIP6 data to the cloud. And I'm just going to go through some slides to motivate all of this at the beginning. In longer presentations, I usually run this live demo. This is a project that I've been working on with my former colleague, Tom Nicholas, where we just sort of said, can we just reproduce an IPCC plot with raw data on the fly? And we can. And it actually only takes a couple of minutes with sort of the full Pangeo stack and the data in the cloud. I cannot run this today. It's a bit short on time, but there's a couple of videos. You can click on the links if you like that. You can also run this yourself if you have some. You can run this on your computer. The data is fully open. It might take a little bit longer because of your internet connection. But I just want to this is sort of like the main thing that I usually show lately. And I just want to sort of always need to take a step back. I do this very often, and so I gloss over this, but I think it's really truly amazing that we can do this now. This used to be a huge effort. And we can just now, basically in the time that it takes us to brew a coffee, we can reproduce these sort of very important plots and then could go and modify them or sort of build on top of them. The other big thing for me is that this makes climate science more inclusive. Some of the examples that I'm showing here is, this is a workshop that we gave at LEAP. And on the right, you can see a climate match. These are sort of open educational programs that basically use the raw CMIP data. I'm basically giving these examples. There's no sort of simplified version of it. Students can learn right from the get-go with the actual data, and then can also keep working on that for a scientific project. So I really think that sort of this really effectively breaks this requirement to sort of belong to a big, mostly Western organization to sort of get educated about climate science and participate in the scientific discourse. And then lastly, everyone wants to use CMIP data these days. I hear from more people from different sort of sectors. This is not just academia, it's also the private sector, the public sector, and all kinds of different stakeholders that they need this data. And I personally strongly believe that it's really better to rally the diverse user community and keep working on improving a single open data resource rather than maintaining multiple repositories for a select few. And while this means that maybe someone might make a buck out of that at some point, I think this is a much better alternative than creating sort of multiple siloed copies, which would, I think, inevitably happen if we don't sort of work together on a single one. There are, however, some pretty big challenges with sort of getting all of this data in the cloud. Like it's pretty big. We're like CMIP is, I think, around 13 petabyte when I last checked, or somewhere around that area. So that sort of leaves the first question. How do we prioritize the most desired data sets? This also means that sort of effectively we have millions of data sets with variable size. Some need some minor fixes to be sort of converted to cloud optimized Zarr stores. While I'm talking about a data set, each of these data sets basically consists of possibly many netcdf files. And that's sort of sometimes some of these are not available on all of the download servers. And each of these data sets will have sort of a vastly different array shape. So we need to sort of accommodate a bunch of different data sets in one common workflow. The last thing I think is sort of that's important is this ingestion is not just sort of a set and forget, like one-way ingestion. We really need to also take care of data sets that have been retracted. We want to like make sure that we really sort of keep the mirror that we're building here like up to date. So I'm going to start with like some history of what has been done. So I think the proof of concept was started a few years ago, and basically the idea was, or what ended up happening is like Pangeo partnered with Google and Amazon to host the data in their respective public data set programs to sort of handle this large amount of data. And I think to this date, we have like over a petabyte in Google public storage. I would have to check that, the very recent one. This whole effort was coordinated between Pangeo and ESGF members. Today, I will focus on the Zarr stores, but you can check the working group website to check out the full list of projects. There were also sort of other efforts going on, and we had weekly calls to coordinate that. And this was all around really great project. I want to give a massive shout out to both the whole Pangeo and ESGF working group, but Naomi Henderson in particular for her sort of early efforts to mostly manually upload a lot of these data sets. She did this based on user requests and basically like put in a lot of manual labor to get this effort off the ground. And then basically we cataloged the data into a CSV file, which is sort of pretty low tech, I guess, but it actually did work quite well. We usually use that with an intake ESM collection. And we also implemented some rudimentary retraction mechanism. And really just like uploading these data early, what I think was what kickstarted a lot of the efforts around this cloud data. Like for me personally, this was sort of, I was exposed to this during a hackathon, and I started working on this sort of package that crowdsources fixes for the various data sets. And I think without sort of that initial effort of just putting it up in the cloud, that might have not actually happened. But then Naomi retired, and we needed to sort of continue these efforts. And so I said, I'm just going to take this over. And well, famous last words. I volunteered to automate this problem, but it actually took a bit longer than I expected. I guess this is something that people know about. But we ultimately, I think, arrived at a process that is workable. And I think I learned a lot through these 2 years. So I think this wasn't necessarily wasted time. It was mostly sort of going back and forth with particular frameworks, and then in the end, really like settling on Pangeo Forge. Like the main thing I wanted to make sure is that we could build a pipeline that would be sort of agnostic of the target bucket or target location, so it could easily be reused or rebuilt if need be. Yeah, so Pangeo Forge, really quickly only, is an ETL tool that sort of encodes all the logic needed to create an ARCO copy, of a data set in a so-called feedstock. The core component of the feedstock is a .py file that contains one or more so-called recipes. This is shown here sort of in pseudocode, just a sequence of transforms based on sort of starting with downloadable URLs to files. And if you want to know more about that, definitely head over to the docs. This is not doing Pangeo Forge justice. I just wanted to sort of do this sort of as a quick intro. My use case really sort of was pushing the boundaries, I think, of Pangeo Forge in the beginning, at least, sort of I think the canonical thing was sort of very large data sets, but few of them. And I think what makes CMIP6 so challenging is that it's actually, each data set isn't that big. It's just a massive amount of different data sets that each one of them had potentially their own sort of quirks. And I think that really sort of the thing that made this all possible is the refactor of Pangeo Forge to use Apache-Beam throughout the whole package. And I just wanted to give a massive shout out to, in particular, Charles, but also all the other Pangeo Forge maintainers for actually making this work. Okay, so I've tried to sort of abstract what I'm doing in my recipe here in this sort of cartoon. And I will go into like some of the details here in a minute. Basically, the basis for this is a list of unique identifiers called instance IDs. Each of these basically uniquely identifies a data set, and each of these data set might consist of multiple files. So the first thing we have to do is basically convert the instance ID to a list of downloadable files. And for that, we're actually querying the ESGF API before we then sort of create a dictionary of recipes. So within this Python file, we're creating a lot of recipes potentially. And each of these are Beam pipelines. And then each recipe follows a set of steps. Some of these are somewhat standard steps that I've sort of abbreviated here. But others of these, and I'm going to go into a bit more detail, are sort of more custom to what I'm doing with CMIP, and I want to disrupt these a little bit more. So first thing we need is actually to dynamically determine a chunking scheme. So since the array is sort of different for each of the data sets, the array shape, we basically need to sort of take that data set, find out like sort of the size of chunks we want and how we want to chunk things, and sort of like do that for each data set when we build each recipe. We then, once the store is sort of like successfully written, log these stores to a BigQuery table, and then can run inline testing to see if some of these data sets actually sort of we're basically checking, can you open the store? Can you actually, is the time consistent, et cetera, et cetera. And then once these tests have passed, we log them again in a different quality controlled BigQuery table. This sort of is quite nice because we don't have to like keep track of it. If this fails out at any point, we can sort of discern that from like taking the difference between these two BigQuery tables and their unique values. Oops. Oh, sorry. Okay, word on the execution of recipes. So the recipe is currently deployed via a GitHub action, the deploy recipe action. The configuration there is fairly lightweight. All we do is sort of provide a configuration files for Pangeo Forge runner, and all the other information needed is encoded in the recipe feed doc. And oops, sorry about that. That was supposed to be that far down. Anyways, so then the action then internally calls Pangeo Forge runner, which is a command line interface to manage Pangeo Forge feedstock and to deploy that recipe to a runner of your choice. We're using Dataflow right now, and this is supported via the Leap project. But basically, this should be runnable on other Beam runners as well. I wanted to like quickly talk about two of the ingredients here in a bit more detail, because I think actually either these could benefit the broader Pangeo community or could really benefit from feedback, or probably a bit of both. So I wrote this sort of like Python client for the ESGF API because everything I found online was actually too slow to like handle potentially thousands of requests at the same time to like build these recipes. And the two sort of main functionalities of this are that you can provide an instance ID with wildcards for each of the sort of facet values, and it will expand that into actually a list of instance IDs. And the other one is that you basically provide an instance ID and you get back a list of downloadable URLs. We're using both of these actually in the recipe as it is right now. So yeah, this is my first actual foray into like writing async code. So there's probably a lot of improvement there if you're interested in this, or if this seems useful for you. You know, please get involved and reach out. Be happy to like chat with people about this. I think the other thing that was might have been interesting for people is the dynamic chunking. So the way we actually implemented this is sort of like the meat of a recipe where you see the actual sort of steps. And if you see sort of this step right here, we can provide a custom chunking function. And all this chunking function does is basically take in an X-array data set. So even for users that aren't particularly familiar with Apache-Beam, this should be easy enough to sort of apply some logic based on the full data set that you're working with. I just put in some nonsense code over here, but then basically just returns a chunking dictionary that maps dimension name to the chunk size. For the recipe itself, we actually sort of I implemented two algorithms to hit what is called a chunk aspect ratio. Oops, I forgot aspect ratio in here. Sorry about that. And this is actually inspired by an idea by Rich that came up during SciPy this year. And basically, like he said, he wanted like for a given data set, he wanted to take a time series, take as long, like X times as long to load as a slice along for, say, let's say X. And sort of assuming that the ratio of load time roughly translates to the total number of chunks along each dimension, we implemented two algorithms, one that only considers even divisions for each dimension, and another one that prioritizes hitting actually sort of that ratio of total chunks along each dimension, but might produce sort of like odd chunks at the end. I'm showing here sort of two examples of the first algorithm, and you can sort of see in the first one, we want sort of equal amount of chunks along each dimension. We're roughly hitting that. There's sort of the requirement there that we have even division, so that will not always turn out perfectly. In the other case, we wanted sort of the y dimension to be 10 times as long, and you can see for the time and y dimension that actually turns out to be quite good for, again, due to the restriction of like even divisions. We're not always hitting this perfectly, but it sort of shows that you can do this. And oops, that one wasn't supposed to be there. And basically the chunk size that we requested is hit pretty closely, and you can play with this, and then we have sort of a tolerance parameter there of like how big or you want to deviate from that value. Either way, I think that's sort of like the sort of pluggable infrastructure basically enables people to like come up with all kinds of their different chunking schemes. You know, you like could imagine, I think one of the things that might be interesting for people is sort of preserve months once like Zarr supports uneven chunking in like sort of fancy calendars, or just like some custom logic for your data set that like based on some existence of one dimension, you want to chunk another or whatever. But like you can contribute whatever you want there. And I think that's actually pretty nice outcome. All right. So, okay. I guess the title was a bit, maybe a bit on the nose. And I guess what I mean by why we should never do this again, I think mostly is to sort of say that this, I very much consider this a prototype. I think we've learned a couple of lessons here. I think the most positive lessons first are just people love this way of accessing the data. I've gotten an overwhelming amount of feedback. I've talked to people, and you know, there's so many people. I think one of the big arguments for me is that I've heard so many people say this was the first time I actually sort of felt comfortable working with CMIP data, felt that it was sort of like quickly usable to like explore something quickly, and that actually made me super happy. But I think we also learned that this sort of work is really hard, and particularly doing really hard to do sort of as a few people operation from sort of the outside. And so we created a branch, and I think much less capable catalog, for instance. I think that doesn't actually measure up to what ESGF is providing. I think people rightfully got impatient when data sets were not up to date in the cloud. I think it just took very long. And people want to sort of like, they see things available on ESGF as netcdfs, and they went ahead and sort of downloaded that data. So I think the conversion to Zarr is just like cost a lot of time and people power. And also we produced a whole sort of, or we're aiming to produce a whole copy of the entire data, or at least like a big amount of it. So I think we should see this as sort of a prototype, and I'm which teaches us valuable lessons for CMIP6, and I'm very sort of convicted to support this for CMIP6. But I think for like looking towards CMIP7, we should sort of think about and potentially not go through with this in the way that it was done before. That's sort of what I wanted to say with like never do it again. I hope that ideally sort of the CMIP7 data, which will be much larger, will be offered in some sort of comparable way from the start. I think important to point out here, I don't think that necessarily that means that, but it could mean that we like serve this through commercial cloud resources. I think this is mostly about sort of the data access pattern. I think people love sort of the streaming Zarr data from cloud-like storage and then sort of using compute of their choice to analyze the data and sort of the decoupling of these two things. So I would really hope that we can sort of gather more support from the community to support a cloud-like access to ESGF data sets from the get-go. I think that really would sort of multiply the user base and with that the usefulness for adapting to human-made climate change. And I think that's in the end like what we all want. But I'm very happy to discuss more on how that could be done. Yeah, maybe after this or sort of offline. Quick sort of like how to get involved. I think like sort of like what the things I think we can do to like push this vision is sort of use this data, right? Like I think that a lot of these times sort of people think this is just I said it's a prototype, but it's like the data is usable. Like there's sort of like I worked on this this paper with a colleague of mine, and basically they use like purely CMIP6 in the cloud data. And really like sort of enabled a really good like workflow between collaborators. It really made like collaborating on the data easy. And please request more data as needed. We're open for sort of requests again. There's still, unfortunately, I wasn't quite able to sort of put this back into the public Google bucket. We hopefully will figure that out in the coming weeks, but we're certainly able to like accept requests. So there might be a bit of a wait time, but like, please go ahead and if you need some of the CMIP data, just head over to CMIP6 Leap feedstock and submit an issue. There's like a template for that. It's all in the README. I really want to push this forward and like enable people to use the cloud data only now that we have all this set up. Also, if you're interested in getting involved with the ingestion, I'm very motivated to push this effort, but time is always, as always, is sort of at a premium, and maintenance is hard. So like happy to like work together with people if folks are interested. And then yeah, feedback, questions, contributions, always welcome. Yeah, I guess like find me on GitHub or Mastodon. I'm not that much on X anymore as I used to be.
All right.